Okay, good afternoon, everyone. I think we can start this final interaction session as far as covering of the last topic is concerned, and this is analysis of open systems. So, as you have seen in this specific set of lectures for the introductory thermodynamics course. The approach has been to develop the fundamental laws in a certain sequence and for closed systems initially. And now that we are done with the closed system analysis, what is done is the same set of laws are now extended for open systems. Now, before we actually get going with the analysis on open systems, normally we spend some time trying to explain to the students as to why an open system analysis is important. And in fact, with reference to mechanical engineering applications, we quote several examples, such as a turbine, a compressor or a pump, heat exchangers, boilers, and so on, and point out that each of these equipments can be analyzed for their fundamental basic thermodynamic performance using the laws that we have developed so far. But at the same time, we point out that these equipment, of course, see mass flow of some working fluid go in and go out. And so this is the first time then we start talking about, of course, the transfer of mass across a certain boundary. And having introduced it in this fashion, then we start formally talking about how we are going to be extending the laws that have been developed so far for closed systems to open systems. So this is just roughly the introductory set of remarks. And I assume and hope that people have seen these lectures 41 through 45, where the open system analysis has been expounded. So perhaps we can directly start the discussion in the sense that if you thought there was something different about how it has been done in these set of lectures, and if so, can you point out what you thought was different and so on. Of course, prior to that, if Professor Bhandarkar or Gaitonde has any other introductory comments, I'll request them to say so. Otherwise, we can get going.
Yeah, nothing from my side.
Nothing from my side either.
Okay, so yeah, Dr. Anandan, please go ahead.
Yes, sir. This analysis of this open system with this inlet plug and the exit plug, it is a new approach. Yes, it is nice one. Okay. Thank you.
Yeah, so with reference to that comment, I can point out, and of course, Professors Gaitonde and Bhandarkar can add to it if they want. Oftentimes, you will realize that students are undergoing concurrently, possibly, a fluid mechanics course as well when they do this thermodynamics course. At least in IIT Bombay curriculum of the undergraduates, that's the case, and so it is instructive to point out if that is the case, if the students are undergoing a fluid mechanics course along with this thermodynamics course. It is instructive to point out the similarity or the same nature of this open system analysis with the control volume analysis that they do there, and point out that the nomenclature is essentially the same. Now, there is a question on the chat from Professor Mathur. Do we really need to derive mass conservation equation? Well, my answer would be that for completeness sake, since in this specified course, if you look at this course as a standalone course, and the fact that till now we have not really talked about any open systems at all. The entire discussion so far has been with reference to closed systems. When we are trying to now go to open systems, perhaps it makes sense to do this for completeness before going to the first law derivation. So this is at least my take. I'll request Professor Bhandarkar.
Yeah, I think it's just the approach because different courses and different textbooks have different approach. I mean, it's not that it's a new approach or anything, but it's just that some other course may be taking another approach. And if you do the mass conservation well, then the first law seems okay, just an extension of it, the way you have done it. And the second law seems even easier when you start doing it. So I think if you do one thing reasonably well, then it should be a good way to go ahead. That's all.
Sir, may I have one question, please?
Yeah, you had a raised hand anyway. Please go ahead.
So, rather, I would like to listen from Professor Bhandarkar, sir. So, in your lecture number 42, exercise number 2, so there is one question about the non-adiabatic turbine. So, in that we have included that the heat loss is given as 50 kilojoule per kg.
Okay.
Right? And you have done the solution. So my question is that if that heat loss is not given and the type of turbine is non-adiabatic turbine, then how we can calculate that heat loss in the same question?
Okay, I think I'll have to look at that question to know what the details were. I didn't get it. So it was a turbine with inlet conditions given and there was a heat loss, or what was it?
I will just read the question simultaneously. The steam is supplied to a turbine with HI is given 3.2 megajoule per kg and it leaves with HE is given 2.5 megajoule per kg. The entrance and exit velocities are 170 meter per second and 280 meter per second respectively. And heat loss is 50 kilojoule per kg. What is the work done? That is the question.
Oh, but this is a straightforward application of the first law in a steady state, isn't it? I didn't. So what is the question?
My question is, if in the same question, heat loss is not given, then how we can calculate that capital Q?
You cannot, unless it is given. How will you calculate? It's just a question where Q is given. Otherwise, for a turbine, our normal tendency is just to go and put Q is equal to 0. That is because that is our main assumption, that the turbine is an adiabatic device. So that's all I can say here, isn't it?
So that's my question. If the turbine is non-adiabatic and if the capital Q is not given, then what we can do in that case?
No, then you need to give me some other quantity. Then the problem is incomplete because neither Q nor W is given. It becomes I won't know how to proceed unless you give me some other quantity, isn't it? Yeah, Professor Gaitonde, I think has a...
Yeah, I'll remind again of what I said in the morning. That first law, whether closed system or open system, is just one equation. And hence can be solved for just one unknown. So if there is a turbine given, the inlet state, exit state, mass flow rate, heat transfer rate, if any, and power output. These are the entities involved, okay, typically. I'm not complicating it with delta EK and delta EP. And hence, if you want to determine power output, then W dot will be the unknown and everything else will have to be specified directly or indirectly. And that is why if you want W dot to be computed, we must know something about Q dot. Either we will say it's an adiabatic turbine, in which case Q dot by definition would be 0, or we will say it is not an adiabatic turbine, but we know this much is the Q dot. Am I clear? Over.
Yes, sir, but in a practical situation, capital Q will also be not available for us.
Okay, if you are looking at a practical situation, then you will have to compute or estimate Q dot knowing the surface area of the turbine, the amount of insulation, something about the temperature profile on the inner part of that insulation, and what is the ambient condition. That becomes a heat transfer sub problem, and you are sort of not really, you are going away from the basic domain of thermodynamics. Over.
Yeah, so once those first law statements and the second law statements, the set of examples that have been described later in the remaining lectures, I think 42 to 45, essentially just utilize those derived relations with the information that has been specified in a given problem, and you go ahead and solve for the quantities that are asked. I think a couple more simplifications are probably provided for some specific problem situations as well, as far as my understanding goes. Yeah, let me comment on the question from or comment from KG classes. We would like to actually refrain from getting into any discussion on the third law of thermodynamics. And in fact, Professor Gaitonde gave a good reason for that in the morning session. So I'll request that we will stay away from that. And I think these videos of our sessions are available. So in case you missed the morning session where he explained why we don't want to get into it, once you get the video, the recording, you can always go through it and see why it is the case. Thank you. Yeah, so my question to participants here is there is a certain manner in which the first law has been derived. Of course, we start with the derivation of the mass conservation equation and then extend it, as Professor Bhandarkar said a few minutes ago, to derive the first law statement for open systems. The specific question that I would like to ask with respect to that is how do you do it in general in the class? Do you formally derive these expressions, or how is it done? That's what we would like to, or at least I would like to know.
Good afternoon, sir.
Yes, hello.
So my name is Tanuj Kumar Gupta.
Yes, please go ahead.
Actually, I want to answer your question that how do we frame the outline for first law of thermodynamics? How do we teach first law of thermodynamics?
Yeah, please go ahead.
So actually, all these laws are nature laws, and we can't prove this mathematically. So when I start with the closed system, because first law is defined for closed system, and then we use the four consequences of first law of thermodynamics, and by using those consequences, we teach the students how can we understand the first law of thermodynamics in easy manner.
So
Because we can't.
can you explain to the participants what do you mean by these four consequences?
The four consequences are first consequences heat transfer is a path function, and number two consequences energy is a property, and the third consequences is property is a point function, and the fourth consequences PMM1 is perpetual motion machine of first kind is not possible. So by using all these four consequences, we can explain the derivation, or actually we can't prove the first law of thermodynamics mathematically, but there are four consequences by which we can explain the students how these laws are used nowadays, and nobody till now can deny with this law with these laws of thermodynamics.
Yes, that is correct. My question really was having stated the first law of thermodynamics for a closed system, which is what we have done till now. Now we are extending it uh, for open systems, and it has been done in a particular fashion in the lectures 41 through 45 in this set of lecture videos. My question was, how is it otherwise done in your way of doing things? That's all. Yeah, even though I typed that response to Junaid's question on books, if you really notice carefully right through the lecture videos, no particular mention of any book has been done. And one of the reasons is, yeah, I think Professor Gaitonde has written the response. What we feel is that, and this is what I have also done when I taught this class last semester, is that we use the framework of these lectures, and as and when required, you can try to bring in any specific reference and point out that to the students. So we don't really necessarily, mention any specific book as kind of a textbook as such. And this is exactly how I think Professor Gaitonde also has mentioned right at the beginning of these lectures, that you can pick your favorites, let us say, and browse through those, see how that specific author or those specific authors are developing the subject, and then decide. So it's an iterative process in some sense. In one shot, you cannot really say that this is what I will utilize and be done with it. For someone like Professor Gaitonde, he has gone through this so many times, and based on that, he has come out with this set of lectures, and that's what we use for our course as a framework. So there is no book that even I will want to recommend that this is the book that you can utilize. Yeah, so TKG, we have mentioned a set of books. I think someone has already remarked that. In the so if you look at the course website carefully, a set of books has been certainly mentioned. Then that's all I can say. Professor Upendra, if you want to comment.
Yeah, none. I mean, there are enough books out there. I think some other books also have been mentioned, and I think most of these we refer to. I mean, we refer to Moran and Shapiro. We refer to Sears and Salinger. We refer to Zimansky. So there are a ton of books, and Professor Gaitonde, of course, has picked up some material from different books, and some is entirely his own style. So I think it's
that is how the course exactly has been evolved. Exactly, that's precisely what my point was. Normally I look at books for picking some good problems for examinations and so on. That's typically the use that I am doing for books. But as far as delivering a course is concerned, it is, at least this course, this is the set of lectures that I will use as a reference. But yeah, going back to my question on obtaining the first law statement for open systems, is there anyone who would like to comment on how they do it, and if they thought the way it has been done here is giving them a different perspective and so on?
Hello.
Yeah.
It's convenient to explain first law for open system if we start from law of conservation of energy. So after introducing the concept of internal energy using closed system and explaining the student that difference between heat added and work done by the system is equal to change in the internal energy, and then if we tell them that if it is not closed system, then whatever energy coming into the system is heat energy, and energy coming in with the flowing of the fluid inside the system, which includes kinetic energy or potential energy or the flow work, is equal to energy going out. And then we can write the steady flow energy equation. Now that's the way I do in the class.
Okay.
The only problem which is faced is uh, the energy transfer by interaction are usually in terms of, say, we write q dot and w dot. So in their terms of time, so it's like kilojoule per second. And the changes in properties usually are mentioned in terms of per unit mass. So most of the time students get confused in that. So we'll have to explain the uh, importance of the amount of mass flow rate going in and mass flow rate going out, multiplying it with the property and then converting into homogeneous system of units.
Okay. Anyone else?
Hello, sir.
Yes, go ahead.
Okay, sir. We can. That's. I'm dealing with the first year student. That is the mechanical branch student, and they usually connect the and I will connect the concept of such fluid mechanics laws like conservation of energy, conservation of momentum, and free energy continuity equation with the thermodynamics. So, is it viable thing to connect the basic concept of fluid mechanics, not the advanced part, the basic part, with the basic thermodynamics? It is viable.
Yes, yes, you can certainly do that. That's what we mentioned earlier. That if your students are already aware of those fluid mechanics ideas, or if they are concurrently taking the fluid mechanics course, you can certainly mention that. That's not a problem at all.
Right.
Yeah, Junaid, you have a raised hand, so please go ahead.
So actually, I would like to request all three of you, including Gaitonde sir, Vandarkar sir, and yourself, just would like to listen from your side, because you people are more knowledgeable than obviously our group. So we would just like to listen from your side what exactly the process at IIT you as a teacher following to teach this particular subject, in terms of like coverage of the syllabus, coverage of numerical, theoretical, then assignments, whatever the practices you are following, please, so that we can implement the same at our end.
Okay, let me request Professor Bhandarkar to respond first here.
Okay, I mean, I can tell you clearly that I just exactly follow what Professor Gatunde follows, and the delivery of lectures, the content and the delivery of lectures and the order in which it is presented is exactly the same as they are there in the video lectures. Of course, those video lectures are broken into chunks of 5 minutes, 10 minutes, 15 minutes. Whereas in IIT we either have 1 hour slots or 90-minute slots, and then we plan accordingly and put those lectures in them. Of course, we have if it is not, I mean, mostly I am now not teaching the flipped classroom mode. We give out regular exercises, and those exercises at the end of the uh, I mean, those are the exercises that have been given to you, and every week we do spend at least a lecture in those exercises, because without practice, I mean, the students coming to the exam, they would be in a bad shape. So, at least with these concepts, it's best to have continuous problem solving. And then our policy has always been to hold a quiz nearly every 2 weeks. Okay, so a quiz or an exam every 2 weeks, so that they brush up everything that they have learned in 2 weeks and come. So we hold close to six or definitely six quizzes, okay, in such a course, so that continuously they are evaluated based on those problem sets, and we come up with brand new problems. I mean, none of those problems are ever taken from any textbooks or from the tutorial sheets. We have to come up with some new problem which tests the students. We think, okay, this is what we need to, but these are just short quizzes, 40 minutes maybe, and just test one recent concept, and this really builds up to our final end semester examination. So I think it's just a process. As I told you, material is the same. We follow a process of continuous problem solving as well as continuous evaluation. So this is a very regular trend that we do for nearly all courses. Thank you.
Yeah, so here one more thing I would like to add is that on the course, that is this workshop webpage, you have been provided these problem sets. And we talked about these problem sets earlier, I think it was today morning, I think. Wherein, what I mentioned at least, that these are the problem sets which we utilize for discussion in class. And in fact, you will see some of these problems have appeared in the examinations also over the last several years. And the idea is that unless students are able to solve, analyze these kinds of problems, their understanding of the ideas and the concepts is not really tested completely. And that forms a very big part of our overall teaching, using these kinds of problems for discussion in the class, which are often called as tutorial sessions. And also based on these tutorial sessions, once the understanding builds, then you use those kinds of problems or slightly advanced modifications of those possibly in the quizzes that Professor Bhandarkar was mentioning, or in the final entrance examination. That is how normally we end up teaching every course that you can think of, not just necessarily thermodynamics, but this continuous problem solving on a weekly basis in classes as tutorial sessions is something that is very, very useful for the students. So that's probably one thing that at least I will recommend in case you are not doing it so far. That's something that you can think of doing. Yeah, Professor Gaitonde, I think you can add to this.
What Professors Bhandarkar and Puranik have said is essentially what we do, but that doesn't mean that's the only way you have to do it. In a university system where essentially the whole performance or major part of the performance depends on the semester end examination or term end examination, whatever you say. At least from the practice point of view, the student should be given quizzes, maybe with 0 weight or something like that. And you should impress on students that although the performance here may not directly lead to a final performance, neglecting this means your final performance would be poorer because you are out of practice. So because many of you will be in a university system where you may not have that much of a freedom to decide when to conduct tests, quizzes, exams, and how to conduct them. That is why you will have to improvise depending on the system in which you work. In the IIT scheme of things, if there are 3 divisions taught by 3 teachers, the 3 divisions quite often are absolutely independent, with independent style of teaching, unrelated ways of evaluation. All 3 will learn the same course, say thermodynamics. But one may have a mid-sem, end-sem, and 2 or 3 quizzes. Another may not have a mid-sem at all, but will have 6, 7 quizzes. So it is left to you. So long as you do justice to the teaching and the students learn, that is fine.
Yes, actually, the main problem is that we do not have sufficient weightage in our end. So everything is decided by the university. So that's actually the problem is lies over here. So because of that only, the students do not take the things the way it should be taken. If we give them some questions, unsolved questions, they will never solve, because they would realize that nothing will happen at their end. But if the same thing is happened at IIT or NIT, so the people would take it very seriously. They would realize that everything would be in the hands of the teacher. He would decide what marks should be given. So that's actually the imbalance in terms of dealing with the students at university level, at an IIT and NIT level.
Yeah, we understand those constraints for sure. What Professor Gaitonde was mentioning is, of course, that despite that, you can try to impress upon the students, that if they undergo these regular problem solving activities and so on, their understanding will improve anyway, and one way or the other automatically they will end up doing okay in the final examinations. I think this is what even I would like to say. Of course, it depends on really the attitude of the students at the end of it, but still one can at least try to impress upon them the merits of trying to solve these problems and thinking about these things and so on.
Let me say something. 2 points. You may say that if there is no credit, the students will not solve the problems. Now, we are generalizing and painting all students with the same color. I'm sure there will be a few students who will be interested, will take the initiative and solve the problem. In a class of 60, even if 10 students, 8 students, even 5 students do it, that's worth it. And if slowly other people realize that, look, those 5 students did the homework, attempted to solve the problem, when they were in difficulty, they talked to the teacher and got an explanation, and this seems to have improved their final examination performance, then slowly others will try to imitate. May not be in the same year, but just the way bad things get handed down from one batch to another batch, I'm sure good things will also get handed down from one batch to another batch. It will be a slow process, but it will happen. If you don't expect any change, then nothing will change. You expect a change, then slowly change will happen. Second point, you say that the rules, etc., are dictated by the university. But remember, university is not an entity which creates rules based on themselves. There is a body of faculty called Senate or Board of Studies, whatever, which in turn gets information and feedback from departmental level, which in turn gets the information and feedback from the faculty. So keep on providing that feedback, putting pressure on your immediate superiors, and slowly things will change. It will not change in 1 year. It will not change overnight at all. But unless you put pressure and attempt to bring out a change, nothing will change. So keep on doing it. Keep on attempting.
And of course, I assume there are a reasonable number of participants here who may be from autonomous institutes or deemed to be universities and so on. And those people, I think, probably have, I assume, a little bit more freedom in terms of administering courses. And so they can probably think about these kinds of measures quicker. In any case, we would like to stick to our stipulated discussion, in the sense that if there are any comments or inputs related to the open systems analysis, we would like to hear from the participants. I think there is a raised hand from Sanjay Geji. Yeah, please go ahead.
Hello, good afternoon all. Okay, coming back to open systems, I have this question in mind. I think in case of a closed system, work done is given by integral PdV for a quasi-static process, and in case of an open system, some books say, I don't know it is right or wrong, work done in case of open system is integral minus integral VdP. And to prove that, they use the property relations by the TDS relations, and they come at arrive at the this work done in case of a open flow system as a minus integral VdP, and it is used in case of analysis of compressors, particularly reciprocating compressors. So I want to know whether it is right or wrong, or how it is right or wrong.
Yeah, so there are several things that need to be addressed in what you just said. I think starting from the statement that in case of closed systems, the work done is PDV. But let me request Professor Gaitonde to do that, since he already has a raised hand on this.
I have been teaching thermodynamics not only to students, but to, through similar workshops to college teachers and all that. And initially, I used to get absolutely thoroughly confused about this PDP, PDV and minus VDP stuff. The first thing is, remember that PDV is only the expansion component of work for closed systems. Now for open systems, again, you may have an expansion component, you may have the shaft work component, you may have other components of work, but why does it become minus VDP? So there was finally, I think I got stuck somewhere with a delayed plane or something, and I started deriving it, and I have a derivation. Finally, it turns out that W dot for an open system turns out to be m dot into something equivalent to integral of minus VDP, provided a number of conditions are met. I have that derivation somewhere. Give me a day and I will put it up on the website of this course.
Yeah, so the way to do it,
easy for me to explain it even with my whiteboard in a few minutes.
Yeah, I will just provide you the outline, Sanjay, how you can actually do it. So in this set of lecture videos, you will see that the statement for the first law for an open system has been derived, which includes this W dot as the shaft work, correct? So it's the shaft work that you are referring to when it comes to that final expression of minus integral VDP. And as Professor Gaitonde just mentioned, there's a whole bunch of assumptions that you have to bring in before you can obtain that. The first and foremost assumption is that the heat transfer that may or may not happen in a situation or a system will be required to be considered as reversible. And then you can replace that reversible heat transfer term in the first law statement using integral TdS, and then you bring in that TdS relation, and while doing so you also get rid of the kinetic energy and potential energy terms as being negligible as compared to the enthalpy terms. And once you simplify this, you realize that the enthalpy will get cancelled, and what remains is only this minus integral VDP. So you can derive it, but then there's a bunch of assumptions that have gone into it, and only under those circumstances that expression as minus VDP, integral minus VDP, is valid. So that's something that is more important to understand, rather than utilizing that expression as some sort of a given expression for the work. Okay.
Yes, sir. Why I'm asking is because many times this is very typical question in many exams. Even in GATE exams, there are questions based on this minus integral.
But as I said, you can derive this in a step-by-step manner, starting with the statement, first law statement for an open system. But then you have to bring in a certain set of assumptions, and only under those set of assumptions this is valid. So that reciprocating compressor that you mentioned, is really, when we say that it's undergoing a reversible compression, only under that circumstances that's valid really.
So sir, in that case,
so this, by the way, if you want to look at this so-called derivation, if you wish, it is outlined in, I think, Moran and Shapiro's book. It is outlined in the chapter on entropy in Moran and Shapiro, if I remember. It's toward the end of that chapter.
Yes.
But you can look at the derivation and see, what all assumptions are required in order to obtain that.
Okay. Derivation part is okay, but just wanted to know whether it is valid or invalid. Just wanted to.
Yeah. So under the assumptions of the derivation, it is valid. That's what I'm trying to say.
And one more.
Yeah. Fine.
One more thing. Just on a PV diagram. In case of a closed system of a simple compressible of a PdV work, it is the area under the curve, and for VDP it goes to area to the left of the curve. So is this concept is also okay, or
it's direct consequence of how you interpret area on a curve from the calculus point of view. That's all.
Okay.
So it is correct. Indeed, it is correct. And how that comes about is essentially, if you bring in the notion of area under a curve, as is learnt in our calculus courses, then you realize that this is how it needs to be. You want to add to this?
No. Regarding compressors, be it I think the particularly reciprocating compressors, the model process they refer to isothermal compression, and for rotary type of compressor they come to isentropic process. So that is also a bit of confusion. Isentropic efficiency and isothermal efficiency for compressors particularly.
Okay, so I actually don't know this for sure, but if you look at that expression of minus integral VdP as the work, for these kinds of systems under certain set of assumptions, mind you, you can then actually work out that if it's an isothermal compression, it turns out that compression work required to be input will be the least. And so that all can be shown, but I do not know why, honestly, I do not know why it is used for reciprocating compressors, and for some other type of compressors, it is isentropic work. Maybe I'll request Professor Gaitonde in case, he's aware from his experience on this one.
Actually, the rigorous development of thermodynamics, as we have been doing, is only in the last 3-4 decades. Whereas before that, energy converters or power plant people have gone ahead with their own interpretation, and hence one of the results has been minus VdP and other, the equations specific to a particular piece of equipment. All those are, if they are correct, they are consistent with the proper thermodynamic formulation. Let me get my VdP note and I'll put it up, and then maybe many of those things can be straightened out.
Okay, thank you, sir. Sir, just one more question, please. Just want to know the reciprocating IC engines. There is bit of contradiction that is it really a heat engine, or it doesn't come under the category of heat engine?
Which engine?
Heat engines. Like a steam power plant is taken under heat engines, because it is exchanging heat with the boiler on higher side, and on the condenser it is rejecting the heat. But in case of IC engine, it is kind of a open flow system.
Yes.
So
okay. Because in fact, the IC engine gets its energy in the form of a stored heat in fuel.
Yes.
The only difference is the energy is released within the confinement of that system called IC engine.
Yes.
And energy rejection is not in terms of heat transfer. I mean, there is some energy rejection through body, which could, but that's heat loss, not really the major stream of heat rejection. The major stream of heat rejection happens to be the exhaust.
Yes.
So we have an inlet stream going in and exhaust stream coming out. You can sort of split these into an inlet stream going in and a pseudo inlet stream going out after the combustion of the fuel, and an ambient stream going in, and it is coming out as an exhaust stream. So actually, in the old days, this used to be explained as an internal combustion heat engine and an external combustion heat engine.
Yes,
when it comes to power plant, we still make that distinction because in applications and others appreciation of the various types of cycles and equipment, it matters. But yes, IC engine, although it's in a different avatar, that's it. And it's not very obvious like a say for example, steam engine where
Mm.
the fuel is burnt and heat is so-called generated in a boiler, then
Mhm.
transferred across the membrane or the boiler tubes
Mhm. Mhm.
into the working fluid.
To
And
the
then
steam.
in the condenser, again, there is a heat transfer surface. The
Hmm.
condenser surface, it
Cooling
is
water is
cooling
it.
water, it is transferred to cooling water.
Hmm.
Steam plant is simpler because each equipment is specialized.
Yes, yes,
And you can see
independent.
the and heat flow rates very clearly. In
Yes.
IC engine, because it is internal combustion, everything happens in a single equipment. The same cylinder piston arrangement has to do the induction process, compression process, combustion process,
Hmm.
expansion, power generation process, and then exhaust process.
Yes.
So it's everything is mixed up there.
Yes, yes.
It's not so easy to appreciate, but yes,
Hmm.
at
Hmm.
the basic level, it is still a heat engine.
Because apparently it looks like the system in a, even for a cyclic device, the system has to come back to initial state. But
Yes, that is
it.
why if you take an IC engine scores or a cycle scores, we
Mhm.
simplify the analysis by considering in the good old days what we used to call air standard IC
A
engine
stand, yes, a standard
and air
cycle.
standard cycle and air standard efficiency.
Yes,
Okay,
yes.
that is one simple step, a simple model by which we convert it into a closed system and try
Mhm.
to extract some characteristic out of it.
Mhm. So in the end, I can say that IC engine, even the gas turbines working on Joule Breton cycle, uh, all those are the category of heat engine, no, sir?
Yes, all those are heat engines.
Yes.
Going through cycles.
Yes, yes.
Okay, okay,
And
okay.
those are because the fuel burns or undergoes process of combustion
Mhm.
in the system. The working fluid is not useful anymore, hence needs to be exhausted or thrown out.
Yes, and
So those are complications involved. Those are open systems because uh,
hmm,
some fluid goes in, just like open thermodynamic systems. These are open cycles.
open cycles. Yes.
In a way, they are cycle, but they are open in the sense the environment and nature is supposed to do the job of cleaning up our exhaust and convert it back into clean air and fuel. Again, some parts may take few decades, some parts may take millions of years.
Yes. Sir, hello, sir.
Yeah, go ahead, go ahead.
Sir, just again, it may be quite irritating to you as I am extending my questions one by one. Just
No,
Not
go
at
ahead,
all.
please, no problem.
The course is for that.
no, but maybe there may be rest others who can. Okay. Now I want to talk about PV panels, solar PV panels, sir. In that, solar radiations are directly converted into EMF. Again, there comes a term called efficiency, conversion efficiency. So, can we solar PV panels converting solar radiations into this EMF, electrical energy? Can we thermodynamically analyze it, or can it be a part of thermodynamics, or it
It can
cannot?
be a
That.
part of thermodynamics, but it's not a cyclic process. So,
Hmm.
and photovoltaic characteristics will have to be involved. First
Hmm.
law of thermodynamics, even second law of thermodynamics is properly applicable, but
Hmm.
the actual detailed analysis becomes complicated because
Hmm.
radiation and thermoelectric and electrothermal effects, all
Hmm.
those Peltier effect, Seebeck effect, all those things will have to be included.
Yes, because okay, this thing you might be well knowing that even for the solar PV panels conversion to electric, I think it is around 15% only, as per my
No,
information.
that is not a energy conversion or a cyclic uh, efficiency. There is no cycle involved there. There are no
Mhm.
two reservoirs, etc. So that efficiency is like our, efficiency of a gear chain or something like that.
Conversion efficiency from
It's a
what?
conversion efficiency. It's not a cyclic efficiency. So do not or don't think it is comparable to Carnot cycle efficiency or our heat engine efficiency.
Okay. Thank you, sir. Thank you.
Yeah, I want to take up that question posed on the chat from Dr. Vanjara. Is it okay to consider closed system as a special case of generalized system where mass exchange is not allowed and then treat the closed system? Any comment on that from others? At least as far as I am concerned, I would not want to do that, and will first really talk about the closed system as it is, the way it has been done here. Only from the point of view of being very clutterless and clean in terms of concept development. That's what my take would be, at least on that.
Okay, sir.
I mean, one can probably put in the effort and probably do it in a very clean, understandable manner. But at this point, perhaps I will not do it myself.
Sir, actually this question was posed once by a student in my class.
No, that's very nice. Actually, one can certainly look at it from that point of view. There is no question about it.
And he also argued that why we are studying closed system first and the open system later, because actually if we see closed system is one of the generalized open system. But I told that this is what the development in first law of thermodynamics. Sometimes it happens that in first law of thermodynamics itself, the equation for the steady state flow process gets derived. As a special case, and again then when we discuss in thermodynamics flow processes, at that juncture we discuss this details of the control volume and those things.
Yeah, I'll still say that from a pedagogical point of view, it is better to do the development first with closed systems, and only when those concepts are in place, then you can bring in the open systems extension. This is what I will do. But that's a nice question, at least from the student. That's for sure.
Yeah, thank you, sir.
Of course, it turns out that in engineering applications, predominantly you will encounter open systems. That's also probably a fact, but still I will say that from a pedagogical point of view, it is better, doing everything for the closed system and then going to open.
Hello.
Yes, go ahead. If no one
Hello,
is,
sir.
if no one else is asking questions, you can continue.
Okay, I'm Sanjay again here. Sir, this question may be somewhat out of context, but through general discussion of people or even students come to me asking that as we are moving towards the age of AI, artificial intelligence, and IoT things, Internet of Things like this, and data science, and lot of things are coming up, and somehow they think, and even now there is a talk of e-vehicles, and in next 10 years or so, IC engines might be obsolete. So there is a notion that what is the use of what is the use of thermodynamics going to be? Why are we taking up? We are discussing all these first law and second law and all. If anyway it is going to be obsolete or so, is that, sir? How can we?
Well, first and foremost, quick comment on the IC engines part. I don't think you will see IC engines go out of use that easily or that soon. It may happen, of course, for passenger vehicles, but for some other types of transportation, it may not happen that easily and that quickly. Probably not in my lifetime, at least. I don't know. So that's just a side comment on it. See, the laws of thermodynamics are universal in the sense that whether you are dealing with an electric vehicle or an IC engine, they are not going to change. Okay. As Professor Gaitonde just mentioned, related to your question on solar PV panels, the details, as to how those laws are going to be applied to the specific system under consideration may change, the details. But the overall idea is not going to change. So in that sense, I think thermodynamics is not going to go anywhere. It will remain as a cornerstone engineering science course and a subject that we will have to deal with. Maybe the contents will evolve over a period of time. But the fundamentals, as far as I understand, will not really change. In fact, I'll ask Professor Gaitonde to comment on it because of his experience on this.
See, the applications may change, but the first law, so long as it represents, something related to energy and energy transfer, all that will happen is the work modes will get added to, subtracted from. But the first law at its basic level remains. We'll have to keep on applying it. So long as we use energy for some purpose, first law will be there, second law will be there. Second law will be there because at a philosophical level, time exists, and hence there will be irreversible things happening. And then second law will be sitting next to us, seeing to it that we do nothing wrong. That's it.
Yeah, Dr. Vanjara, you have your raised hand, so go ahead. And related to your other point on artificial intelligence or machine learning, etc., I am not really in a position to comment as far as its utility on thermodynamics issues is concerned. So I will not be in a position to comment. Yeah, but Dr. Vanjara, go ahead.
Oh, sorry, sir. Actually, my mic was muted. I was not aware.
Yeah, no, go ahead, please.
Yeah. Professor Gaitonde has actually given the answer that thermodynamics of the fundamentals will remain as it is, and they are universe. The applications, some applications might be having presently more value, but like in our branch of chemical engineering, it's having so wide application to find out the maximum extent of the reaction and separation both under idealization, like destiny, which leads to phase equilibrium and chemical. So as until and unless there are reactions and separations, the applications of the thermodynamics will remain. Okay, so there is, I think, the base of the thermodynamics will remain forever. That's what my opinion is.
Yeah, thank you. Yeah, so a general comment, now that we are inching toward the end of this workshop, is that one aspect that we would like to emphasize is the use of problems to illustrate the concepts, to reinforce the concepts. And these problems can really bring in real life systems and appropriate simplifications of those real life systems. And that's something that gets appreciated from students quite a bit. So these are not necessarily only academic type problems or questions, but taking up on a real life system and trying to simplify it to fit our way of analysis. At the same time, the simplification should not really be so much that the meaning of the real life system is lost. It's an art really to generate these kinds of problems, but with experience, I think one can do that, and that's one of the suggestions from our side. In fact, that's what Professor Bhandarkar kind of hinted earlier when he said that we keep sort of generating new types of problems which will still utilize these fundamentals, in terms of applications of these laws and so on, but for possibly slightly different systems and so on. So that's one thing that as teachers we should be trying to do. There are ways in which you can try to figure out how to generate new problems and so on, but that's one point I wanted to make here as a general point. Yeah, Naren, your comment is well taken, certainly the last one at 306. It takes a bit of an effort, of course, to generate problems of the kind that you are mentioning, but it is certainly a worth exercise. both for students and more so even for teachers, in order to improve our own thinking and perspective on these things. So I will certainly say that your point is well taken.
Okay, thank you. So
And
may I just
also, yeah, please go ahead. Sorry, yeah.
I just want to add a statement. So to begin with, instead of giving problem statements, what once I tried is I actually solved. Right? I don't give the statement sheets to the problem question sheets to the students. In fact, I wrote the problem statement. I solved them. Let's say each sheet will have like something around 3 or 4 problem sets. One A4 sheet back to back. Some of the problems are solved correctly, some were not solved correctly, and the task for the student is to identify whether I have solved correctly or not. So in a sense, they will evaluate, all students will evaluate in groups, or sometimes it was an individual activity. So they need to find out whether the question was solved, or the problem statements were solved correctly, or it was otherwise found. If it was incorrect, then they have to find out why it is incorrect and how it can be solved better. So it's a kind of spotting the error in the problem sheets. I agree.
Certainly, that's a good one.
I have to do more work, but I enjoyed it. And the driving force for doing this is very simple. Because if students write answers in their examination answer sheet, I mean, when they provide solution, we find the mistakes, right? But ideally, they should be able to find their own mistakes, right? Once they are graduated, right? We cannot go with them lifelong and then say that, okay, this is wrong, this unit conversion is wrong, here you didn't do whatever multiplication, addition, something like that. It is very primitive mistakes also, whatever it may be. That means they need to develop the skills of finding whether what they have given as a solution itself is correct or not, right? So that part cannot be with the teachers. That also has to be transferred to the students. And if you have to transfer them, then they need the practice. And another thought process why this I brought up today is, typically a human mindset is very active in finding flaws rather than finding the other way around. So that's what I just reversed it, and I just want to know if somebody has used it. Thank you.
Yeah, thanks very much. And the follow-up comment from Dr. Salil Ismail on your comment is also well appreciated. Yes, I think each of us has indeed its way of doing things, and often the interested and careful students have pointed out what has been the mistake that you have done and so on. So very true, and I think it helps the students to think also in one particular fashion, to point out what is wrong, what is right, and so on. Very well said. So I think Junaid has both Sanjay and Junaid have raised that. Go ahead.
Yes, sir. Sir, one question that is just for my understanding. Suppose we have one holographic display or something like virtual reality environment. Then that would be which type of system? Either open or close?
No, sorry, say that again. I actually didn't hear the first part at all.
A holographic display of something.
Holographic display of something.
Is which type of system?
I mean, as long as you can say that there is no mass flow rate that is going in and out, you can call that as a closed system. Of course, you need to define your boundaries correctly and so on. But that's what my answer would be. I will request Professor Bhandarkar to comment on this.
Yeah, I would say the same too. I mean, if you are not inducing a flow at all, I would just stick to a closed system and finish it. Yeah. I mean, that would be the analysis. I mean, see, finally you have to come up with a way to analyze. And I would say that yes, analysis as a closed system would. But what is it that you want to get finally is of course another question. But yes, this will be analyzed as a closed system.
But suppose one object is there and we are displaying a holograph of that particular object. So by using some other system, so can it be called as open system because we are using something in terms of energy to display that object?
Well, of course, Professor Gaitonde has remarked that virtual reality is the only place where the laws of thermodynamics may be violated. As long as you want to try to fit this within the definitions that we have for our systems, I will still stick to my answer that as long as you define a boundary for your hologram system, and if you realize that you cannot identify a mass flow rate of any kind going in and out, I will stick to that being a closed system. Okay, let me also point out that given the time that was available in this workshop and to have some meaningful discussion, the three of us identified probably the most common topics that are covered in this thermodynamics course across a bunch of institutes and so on, and that's what we have identified. But as I mentioned already, there are a couple of weeks of lectures on introduction of properties of working fluids such as ideal gas and water stream system. So that's also something that I would request all participants to look through, since these lectures are going to be available to you later as well. The main utility of those will be, in generating problems wherein the applications of these first law and second law in particular can be worked out. And also there is one topic on property relations, which is something that we haven't talked about here, and that's a little bit different from the other topics that we have seen so far, in the sense that has more mathematical base, specifically partial differentiation. We didn't want to take it up in this workshop for explicit discussion because I think, as far as my understanding goes, there are enough places which do not really include that topic to in the course. But I would still recommend those lectures to be viewed, and if you think that material can be seamlessly incorporated in your course, you can certainly do that. Yeah, Professor Gaitonde, please go ahead. Yeah.
Professor Puranik mentioned that in this 3-day workshop we didn't bring up the property relations chapter or property relation theme, but that is very important part of thermodynamics, and some of those things are really surprising, that how we are able to relate and extract relations which are unimaginable in our routine derivations. And also in particular, we keep on using PV diagrams and TS diagrams, merely, not only in thermodynamics, but later when it comes to power plant cycles and analysis of open systems. It is only when you study properties properly, you will appreciate the links between a process or a figure on a PV diagram and a process and a figure on the TS diagram. In fact, those who have studied property relation should appreciate that Maxwell's relations are nothing but a embodiment of the hidden relation between PV and TS diagrams for a simple compressible system. Thank you.
As a side note to that, please go through those lectures, and you will also realize that one utility of those would be to point out that when students go through the calculus course initially in their engineering time, And oftentimes, students have this question: where is this stuff going to be utilized? And this is one immediate, place where you can point out how the partial differentiations, at least that they learn in calculus, um, get utilized, so that there is some. What should I want to say here is that there's some utility of what they do in the engineering mathematics course, as it relates to engineering subjects, is what you can also try to find out.
Hello, sir.
Yeah, go ahead, please.
Sanjay here. It's again my personal doubt as a student. Sir, I just want some discussion on vapor pressure phenomenon. Vapor pressure of a fluid or liquid rather.
Can I request either Professor Gaitonde or Bhandarkar?
Sorry, what was the question? You want to know about vapor pressure?
Yes, sir.
Yeah.
Vapor pressure of a liquid. That
So
phenomenon.
as a phenomenon means you want to know why it comes about, or?
Yes, sir. Because in many books, I think it is mostly in fluid mechanics books, vapor pressure phenomenon is explained like this: you take some water in a glass half filled and put a lid on it, and after some time, there are some vapors generated, and it is the pressure generated by the vapor itself on the free surface of the liquid. So it is something like that, and again, extending further, vapor pressure has relation with the saturation pressure or boiling pressure that we say. So all those concepts are same or different terms?
Yeah, see, normally at any time, if you have a liquid, it will have a tendency to evaporate. I mean, in the sense that the liquid on the top layer, the way people look at this is that from the liquid state it goes to gaseous state. Of course, the reason is that the molecules on the top, they can escape faster, okay, because they are held only from one side. But after a certain point, once they are there, of course, the molecules are continuously, if let's say it's some liquid, the molecules are in the air, they are continuously also hitting the liquid, and they can get captured there and get back into the liquid. So at a certain point, there is some sort of an equilibrium, and that would be the vapor pressure, which is so the vapor of that particular liquid you're looking at would be out there. So, and that is normally called the vapor. I mean, I think as far as I know, this is the explanation that is given in probably school textbooks, and for me also, this is about the explanation I know. But for every pressure, there is a saturation temperature when you can saturate the whole, or let's say when the vapor pressure is equal to the saturation pressure, it's when you have again some kind of the liquid leaving and getting into the gaseous state, and that is where we call it as the boiling point. So this is roughly my understanding. I don't know if Professor Gaitonde has to add something onto this.
Actually, there is a discussion of this in the the properties of steam lectures. Either you may see Professor Atre's lectures, or today evening I am going to give you a set of links for thermo course we had some 10 years ago for teachers, in which I don't know whether I taught it or UVB taught. Another way of looking at it. And the way we teach, or at least I teach, is I start with the phase diagram of water, ice, and water vapor, that is steam. And all these ideas slowly get clarified out there. Actually, what the chemist vapor pressure is our saturation pressure, or properly the saturation relationship between pressure and temperature for a liquid and its vapor in thermodynamic equilibrium.
So, sir, hello. So the general observation is that whenever we have some water in a glass, and we put, and there are vapors generated, and after some time they condense over the top on the topper part, upper half. Okay. So that vaporization process, does that depend on the temperature of water and the surrounding conditions? How is that, sir?
That is a very simplistic explanation. Actually, if you have an open glass, then it is not a simple water and its vapor system. You have the air also present there.
Yes, yes, sir.
Whereas property ordinary water substance or properties of water, steam, ice, we consider a closed system containing only, the H2O or the naturally available H2O.
Pure substance.
We don't only when we come to psychrometric, then we consider water vapor and air meters. So initially we talk of only purely water systems, or so-called what you say pure systems or pure substance.
Pure substance.
Then we have a simple phase diagram because concentration is not involved. And then we find that the vapor pressure and saturation pressure are essentially the same.
Yeah,
that is thermodynamics, but then we are going into properties of material. And we'll have to bring in, phase equilibrium and phase rule and such stuff.
Sir,
yes.
Can we discuss a little bit about thermodynamic wet bulb temperature?
Not here.
Cannot. Okay.
Yeah, see, that part on psychrometry is something that we don't really, include in this first course, and that's something that we would like to stay away from, if you don't mind.
But sir, thermodynamics is anyway involved, no, sir? Because
I agree, but that specific topic is something that we do not include in this first course on thermodynamics. If of course you can look into the set of textbooks that have been mentioned, including Moran, Shapiro, and Van Pelt, etc. And I think you can go through that material from there. That's what my request would be.
Because in that my question was like this: when we record the wet bulb temperature with the sling psychrometer, the sensing bulb, thermometer bulb is covered with the wet wick, and that is carrying some water, and it is we rotate it at some velocity, at some speed, so air blows over it. So while analyzing it, my problem or my struggle is to analyze it thermodynamically, how to set up the system boundary over there. Is it the bulb is a system or a wick is a system? That is the problem. Or when that temperature reading that we get on a thermometer, whether it is the temperature of
it's a good valid question, but unfortunately I'll repeat that we will not really address that. Please look into the references, the standard textbooks on this, and maybe offline we can take this, but not here.
Okay. Thank you, sir.
So one point that I would like to mention from the previous session, and that is when Professor Gaitonde mentioned that lecture number 29, where related to second law and after the introduction of the notion of entropy, the three words isentropic, adiabatic, and reversible have been mentioned. So I am on behalf of the other two instructors expecting that as part of the graded activity, each of you will be able to generate a good question on that specific aspect, which will test the understanding of students. So I hope to see when you submit your graded activity, which by the way has now been extended. The deadline of that has been extended to Wednesday, I think 24th, 12 noon. And so you can take some time, think about the issues that have been discussed here, and come out with some good questions or problems which you can submit as the graded activity. So I thought I'll mention that now. Yes, there are 5 because there were 5 interaction sessions. So there are 5 graded activities. Yes. Yeah. So I think as we start winding down, my request to all participants would be to again, think about the objective of the workshop. what was the basic objective of this workshop. And each of you are experienced or is experienced in teaching this subject. We have presented one way of teaching this course, as we have been doing at IIT Bombay for a number of years. And again, I'll repeat that, it's just one way of doing it. However, the reason we want to do it in this fashion has been, explained, I hope, repeatedly in some sense, that we want to present the material in a consistent and unambiguous manner, without getting stuck into any circular sort of arguments. So my request would be to think about that as the overall objective, and to see how you can now point out to us in the last session for about an hour or so from 4:30, what really that you would like to take from this workshop, and by providing possibly specific examples where you would like to incorporate any of the material that we have gone through, or anything else that you can think about. Yeah, Professor Mathur, I think we had tried to communicate to all participants sufficiently in advance that it would be nice to go through these video lectures. Maybe there was not enough time that was provided. I understand that, but it's not a problem, because I think many of you probably have noted down many things during the last 3 days of discussions, and you can always go back to those videos now because they'll be available to you. And once you go through those again, you can look at what you have noted down during these 3 days and think about those issues, and see if you want to make some more use of those videos in your respective courses. So I don't really see too much of a problem even if you didn't get enough time to go through this video. That's what I wanted to point out. Yeah, one other sort of more philosophical point of view from this pedagogy is what I would like to point out. Again, the IIT Bombay scheme of things, in particular, is that we would like to focus on fundamentals and making sure that the students understand the fundamentals as clearly as they can, and the remaining things should take care of itself or themselves in some sense. So for example, with reference to this particular course, there is a follow-up course in the third year, in the 6th semester, in the undergraduate curriculum on what we call applied thermodynamics, where topics on power cycles such as Rankine cycle, the Brayton cycle, and the refrigeration, air conditioning, psychrometry, some basic aspects of combustion, and some issues related to IC engines are discussed. But if you think about those topics, those are merely straightforward applications of the fundamentals that have been set in this basic thermodynamics course. And that is how we would like you to also perhaps think about those additional topics. You could include those in this current course as well, or have a separate course altogether, which should become fairly straightforward once this fundamental course has been in good shape. Professor Upendra, do you want to add to this, if anything?
No, that's fine.
Okay. Yeah, regarding your IIT Bombay X login account, I will ask the workshop staff to respond. I don't know what are the policies on that. They will be able to tell you. If is one of them around, Urmila or somebody? Yeah, Urmila is around, I think, if she can answer that. One way or the other, you will know from them. Okay, so as Professor Gatonde has remarked, it typically remains alive, so that's not a problem.
Yeah, I think the IIT Bombay X site is modeled on the EDX site, so you can create a login anytime, and whatever is available, at least in IIT Bombay X, is just available permanently and free probably, and EDX is probably EDX has some distinction between some courses, but many courses on EDX are similarly available free. As long as they are there on the web, they are available free if you want to just check them out. Yeah.
So can we hear from some participant who hasn't spoken much during this workshop in the last 3 days? You are welcome to do so. Please go ahead. On the question on further workshop on applied thermodynamics, etc. As of now, there is no plan, but we can think about it certainly, and will be announced in time if one is planned to be offered. Again, the same response to the question on workshop on heat transfer. As of right now, no plans, but some of our faculty have offered these on NPTEL. In fact, there is a version of heat transfer from Professor Gaitonde and Professor Sukhatme on NPTEL. There is a good chance that many of you may have seen it as well. Yeah, so maybe Professor Gaitonde only can comment on that.
See, that means Professor Sukhatme and mine heat transfer lectures are there on the net. NPTEL, they are available on the YouTube site. You simply put Gaitonde heat transfer or Sukhatme heat transfer and you will get the whole series. You may have to search a bit though. The only thing is these are about maybe 14, 15 years old now. So some amount of staleness has set in, but the basic principles remain the same. Particularly when two things, particularly when it comes to convection, we have newer and more useful and widely applicable quote unquote better correlations available now. And the second thing is the treatment of radiation has undergone a total change in the last 10-15 years. So I myself consider that treatment of radiation to be a bit archaic now. But otherwise, for a general audience, as a first resort, those are okay. And I'm sure there are other more modern versions of heat transfer lectures available on the net. I have not searched for any recently, but I'm sure they are there.
Yes, I'm also sure, even though I haven't seen myself. There will be a lot of let me take that as a point of departure and point out that even for thermodynamics, please go through other material that is available, both in terms of videos on say NPTEL or Swayam or one of those platforms, or anything that you can think about. And all that we have tried to point out is one way of doing this course, which in our experience has been appreciated by students a lot. And in fact, one comment that I think we normally hear is that after this course is done, students seem to, typically the experience is that something is done in one semester and you go to the next semester and students often seem to have completely forgotten that matter, or the stuff has completely evaporated from their brains for whatever reason. But with this course, it's my experience that students seem to understand this way of development of the subject very well, and it remains in their head for a long time. And that's one characteristic of this specific course that I would like to point out. Yeah, Professor Gaitonde, go ahead.
So see, the course of thermodynamics, not only, I'm not talking of the way we taught it. The course of thermodynamics has very few principles, but lots of derivation and applications. And the basic understanding requires just, first law, zeroth law, second law. And everything follows in a nice structural, or can be made to fall in a nice structural, logical manner. Perhaps that is the reason why students who study thermodynamics reasonably well tend not to forget what they have learned.
Yeah, that is quite likely, yes.
Perhaps that is one of the reasons why I initially as a student got attracted to this, and then as a faculty continued my interest in teaching of thermodynamics and also later applications of thermodynamics. Thank you.
So in fact, what I will suggest now is, if there are no further specific questions, we can wrap this up a little earlier. And I will request the participants to think a little bit in the next 45 minutes or so when we convene for the concluding session, where only the participants will be requested to speak one by one, where what we expect is what is it that they can point out as one or two main takeaways from this workshop, and specifically in terms of teaching or pedagogy of this course is concerned. What would they like to do when they go back and the next opportunity of teaching this course comes their way? So that's something that I would like to request all participants here. And so when we come back at 4:30, this is how we will take that session up, and we will request people to speak for a couple of minutes to point out at least one or two things that they thought was very useful, say, from this workshop, which they can incorporate in their way of teaching thermodynamics. So, Professor Upendra, you want to add to this?
No, not really. Yeah, I think that's fine.
Okay. So we can quit now and reconvene in about less than 45 minutes, in about 40 minutes for the final session. Is there any other announcement from the workshop staff, Urmila? If you have anything, or Mahendra, if you are on this in this meeting, please go ahead and mention that.
Only hi, Kalpana here. So
yeah, Dr. Please go ahead. Yes.
So we will be having a feedback form also. So that also we will be posting it on the chat, as well as we will be posting it on the course. So I request everybody to fill that also, apart from the feedback which you will be giving us in the next session. Thank you.
Yeah, that I just to reinforce that point. Please fill that feedback form as candidly as you can. That would be very good for us. Thank you.